So how to find the interior point of a set, or if any element of a set is given to you, then how you can come to know whether it is an interior point of a set or not. Before we actually get started, we should define our interior point. So if A is any subset of X, then P belongs to A is interior point of A if there exists open set G containing P is a subset of A. What does that mean? I mean that if A is a subset of X, then P is a interior of A if P belongs to an open set which is a subset of A. Then over P is a interior of A. Interior point of A. Exactly. So the interior point is oftentimes denoted by A naught or interior of A, as I written here. Okay. So this interior point has a very, very, very close relationship with a neighborhood. How it has a close relationship with a neighborhood? Exactly here, as I say, P is a interior point of A, then this A is an neighborhood of P. Neighborhood of P. Okay, so we can write that the reverse of interior point is neighborhood. You can see that from the above example. Interior point of the reverse of interior point is neighborhood. Is neighborhood. Is a neighborhood. So if I can find a neighborhood of any set, then indirectly I can find the interior point of that set as well. So in the last lecture, I explained that the closed interval AB is an neighborhood of open interval AB. So the interior of closed interval AB is equal to the open set of AB containing that endpoint. Similarly, as I explained in my last video, that the neighborhood of each open interval, each point in an open interval is the whole open interval. So the interior of A, B, which is an open interval, is whole open interval. Similarly, I can find a neighborhood of every point in real line. So the interior of A is equal to whole number line, because I can find neighborhood of each number in number line. Similarly, as you can see that I cannot find the neighborhood of rational numbers, because between any two rational numbers there exists a rational number, but there exist also a lot of irrational numbers. So I cannot find a neighbor of rational numbers. Okay, so the interior of the rational numbers is empty set. Similarly, same goes with the irrational number. So the interior of the irrational number is also empty set. Similarly, I cannot find the interior or the neighborhoods of natural numbers. So the interior of natural number is also empty. Same goes with integers. The integers set has also the interior empty set. So I hope you understand this, and these are the very, very important points about interior points. You can take the screenshot of it. If you do not want to take screenshot of it, then the lecture notes of this lecture is available in the description box, and the link is given in that. So go and check it now. Okay, we are going to find a very, very important example related to it. First, we change it over color because white. Okay, so as explained earlier, I have a subset A of X, which is given to me, which is this. This is the subset of A, which is given to me. Now I take elements of A, and now I take the elements of A and try to find the open set. And how open set I can find by tau, because in my first video I explained that tau contain all the open sets. So the open set I want to find are taken by over tau. And then in the end I take the A. This I think I will try to do. So how I can do? So I have the set A is equal to A, B, C. Now I take first A, then B, and then C. So A belongs to A in tau. A in tau. Similarly, A belongs to AB as well in tau. Similarly, A belongs to ABC, ACD, CD. Similarly, A belongs to AB, A, B, C, and D. Similarly, A belongs to A, B, and so these are all the open subset containing A in tau. So next step is to find that open subset which is a subset of A, and A is equal to ABC. Similarly, AB is equal to ABC. A is equal to okay, ABC. Now I'm writing this. And similarly, A, B, C. Now A is a subset of ABC exactly. As A is a subset of A is a subset of AB, so ABC I can find one interior point. Now, as AB is subset of ABC, so this is also satisfying our condition. But the second thing is ACD is not a subset of ABC. So similarly, ABCD is not a subset of ABC. Similarly, ABE is not a subset of ABC. So as I find two open subset which is a subset of A, so A is an interior point of A. Now I repeat the same process for B. Now how I can for B like this? So B belongs to open set AB. Yeah, this, and B also belongs to A, B, C, D. Similarly, B belongs to A, B, E. These are three open sets containing B. Okay. Now the subset of ABC over A. Similarly, subset of ABC. Now we're checking that all these open subsets are subset of A or not. So we should change first. That's so AB is a subset of ABC. Exactly, it is. But ABCD is not a subset of ABC, and ABE is not a subset of ABC. So B is also interior of A, because we find one open set which is a subset of ABC over A, interior point of A. Now we check the same thing for over C, and C belongs to our open set A, B, C, and D. Similarly, C belongs to A, C, and D. So these are the two open sets containing C. Okay. So a subset of AB, C, and the subset of A, B, C. So now you can see that A, B, C, D is not a subset of A, B, C, and A, C, D is also the not a subset. So C is not interior point of A. Interior point of A. So the set of interior point of A are A and B. So this is a very, very important thing. You can check the interior point of any set by using this method, which is, I hope you understand the method and the concept of this example. Okay. Now we are going to solve and very, very important prepositions and theorems related to interior point. So the first theorem of preposition is the interior of a set A is the union of all the open sets of A. Okay. Means that the interior, that means that A interior is equal to union of all open sets. In this example, means that the interior of set A is the union of all the open sets. So I represent open set, the union of all the open set by Gi. So we want to show that A interior is equal to open set. So how we can solve this? We will solve is by this. Okay. So let okay, very sorry. Okay, let Gi be the collection of the index set Gi be collection of all the open sets, collection of all open sets of A. So I have taken Gi, which is a index set Gi, which is the collection of all the open sets of A. If X belongs to A interior, I should bold them. If X belongs to A interior, then there exists I naught, which belongs to over Gi naught, which is a subset of union of all Gi. Okay, so it means that X belongs to Gi naught. As Gi naught is a subset of Gi, this implies that x belongs to the union of or gi. Okay, as x belongs to gi but x belongs to a interior, and this by this I can say that a interior belongs to the union of gi. This implies that a interior is a subset of union of all gi, and here the union of all gi is over open subset. So it means that a interior is a subset of all the union of all the open sets. Now on the other hand, if y is any element belongs to the union of gi, then as y belongs to the union of gi, then y also belongs to gi naught. Exactly, as x also belongs to gi naught. This implies that I should write it here. Okay, then as x belongs to gi naught, then y belongs to a interior. Okay, this implies that the union of gi naught belongs to a interior. So this implies that union of gi is a subset of a interior. So from this equation 2 and from equation 1, G interior of A is equal to the union of Gi, which is the union of all the open subsets. So in this example, we particularly use the equality of sets, where I want to show that if A is equal to B, then I have to show that A is a subset of B and B is a subset of A. I have same example and same pattern I have followed in this theorem. I hope you understand the example, you understand the pattern of. Now the first and the second theorem is that. So next theorem is the interior of a set A is open. So we want to show that A interior is open. For this, we'll suppose that suppose that A is open. We have showed that suppose that A is open. Then X belongs to A. Then X belongs to A. Then there exists open set A such that X belongs to A and each open set is a subset of itself, then it implies that set A is a subset of A, then it implies that A is a subset of A interior. What we have done here, we want to show that A interior is open. We have supposed that A is open, and then we take any element X belongs to A, and there exists an A which is an open set. So X belongs to A, and A is a subset of A itself. So A is subset of A. Then A, as I find open set, so A is a subset of A interior. Okay, this is example number 1. So equation number 1. But we know that A interior is a subset of A. Always remember that A interior is a subset of A, and we prove this thing that A interior is a subset of A in our next theorem. Then from 1 and 2, we can say that A is equal to A interior. As A is equal to A interior, so as if A is equal to A interior and A is open, then A interior should be open. This implies that A interior is also open. Okay, this is a very nice theorem. Our next theorem is the interior of a set A is the largest open subset of A, such as G is an open subset of A. So we want to show that as A interior is a subset of A interior is a subset of A, but this A interior is the largest open subset, of A. We actually prove that. So how we can prove it? We will prove it as if let that index set U alpha, where alpha belongs to I, be the collection of all the open sets of A. B, collection of all open subsets of A. Okay. Let X belongs to U alpha. X belongs to the union of U alpha, where alpha I belongs. We have taken any element X and which belongs to the union of all the index set of U alpha, where alpha belongs to index I. Okay. Now as X belongs to all the union of all the UI, then it means that X also belongs to U alpha. If it belongs to there its union, then it means that it also belongs to U alpha. Okay, as alpha belongs to, then it implies that U also belongs to okay, and this U alpha, where alpha belongs to I, is a subset of A, because set A is the collection of all the open subset. So this open subset is also a subset of A, as I explained in the first line. So this implies that our X belongs to the interior, as I have found a open set between A and between X and A. So X belongs to the interior. So as X belongs to the union of all open subset, this implies that union of all open subset U alpha, where alpha belongs to I, is a subset of A alpha, which is our equation 1. Okay. Conversely, 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 let X belongs to interior of A. Okay. If X belongs to the interior of A, then there exists U alpha, where alpha belongs to I, is an open set, is an open set containing X. This implies that X belongs to U alpha, where alpha belongs to I. As X belongs to U alpha, then X also belongs to the union of U alpha. Okay? Alpha belongs to I. As X belongs to union of all alpha, and in the first slide, X belongs to the interior of A, then it implies that A interior is a subset of union of A, I, where A alpha belongs to over I, which is equation 2. So from 1 and 2, from this 1 and 2, we can say that A interior is equal to the union of all open sets of A. Since A interior consists of all the union of all the alpha I, since A interior containing all union of all alpha I, union of all alpha I, where I belongs to I, is the open largest open subset of Y, as it contains all union of all the open subsets. So it itself is the largest open subset of A. So it's a very, very important proof. I hope you understand it. So our next theorem is the interior of a set A is open if and only if A is equal to A interior. Okay. So it means that the interior of a set is open if and only if A is equal to A interior. In the first slide, I have written that the interior of open interval A and open interval AB is the open interval AB. And in the first slide, I have also written as the interior of the rational number line is the rational numbers itself. Then it means that if from this theorem, I can say that open interval AB is open because its interior is equal to itself. As you can see. Similarly, I can also say that real number line is open because the interior of it is equal to it. I hope you understand this is important. It is a very important point. Okay. So we are going to prove this theorem that interior of A is equal to A if and only if the interior of A is open. So let X belongs to A. Okay. So okay. So let's suppose that before that we suppose that A is open. A is open and let X belongs to A. Okay, as this implies that as every element is a subset of itself, then X belongs to, then A is a subset of itself. A. This implies that A belongs to A interior. Okay. Okay, this implies that set A as X belongs to A is a subset of A interior. Equation 1. But we know that, but in the last example, we have proved that A interior is a subset of A. So this is an equation 2. So from 1 and 2, A is equal to A interior. We have proved that. Okay. So converse, we have also proved, we have also to prove its converse because of the condition if and only if. So conversely, if A is equal to A interior, then since A interior is open and A is also and A is equal to it, so this implies that A is also open. Because A interior is open and A interior is equal to A, this implies that A is also open. I hope you understand. And the all the topics so I have explained in this video. If you have any doubt about it, you can ask your doubt in the comment box below this video. Please like, share, and subscribe our YouTube channel, please.